Hello everyone. I hope you all are doing well. This side Priya Bhatia. And in this specific video, we are starting our very new module. See, until so far, if you will be able to observe in the course, we have covered up the supervised learning module, right? Where we have seen that whenever a label data is available to us, that kind of training of data is what we call as a supervised machine learning, and we have a separate varieties of algorithms for that depending upon what kind of problem we are solving. If it's a regression specific problem, means if our target value is a continuous value, then we are classifying it as a regression. Otherwise, if it's a class discrete value, then we are classifying it as a classification based problem. In our previous sessions we have seen about different varieties of algorithms, but now in this module we are talking about ensemble technique. What is the meaning of that? Although in random forest algorithm I have talked about this a bit, but I think now it's the time that we should deep dive into this specific algorithm, because in the real time when you will go for the practical implementations per se in the projects, industry level projects I'm talking about, you will observe that you are solving a lot many number of times these ensemble techniques only. You are trying to apply the ensemble algorithms only. What is the meaning of ensemble? Simple meaning is that, instead of relying on a single model to give us the result, to give us the outcome, to give us the prediction, why not we will try to curate multiple models, and then we will see that which particular output is the maximum, you can say people are saying, maximum models are saying. For example, if you remember random forest algorithm, what I told you at that point of time, it's a part of a bagging technique which comes under the ensemble technique only, where we have multiple decision trees which are playing a role. And let's say if we are talking like 10 as the number of estimators in the random forest, it means that 10 different decision trees are working internally. They all will give us some prediction, and if it's a classification problem, then we will be able to see the majority voting, means maximum predictions whichever is the same. For example, if let's say out of 10 decision trees, 6 or 7 decision trees are saying that the outcome will be 1, and 2 or 3 are saying the outcome will be 0, so definitely the final prediction will be 1. If it's a regression problem, we said that take the average. So what is happening? We are trying to not rely on a single algorithm per se, single model per se. Instead, we are saying that why not to ensemble multiple algorithms, multiple models in one of the main model, right? So there we will be having one base model, and then on basis of that we were trying to get the predictions, right? Now, this is something which we will deep dive into in this specific module. And you will see that there are 3 specific things which I am talking about in this module. One is the bagging technique. Random forest is also a part of a bagging technique, by the way. But here I'll just show you the demonstration that apart from applying the decision tree, which is there in the random forest, we can apply other algorithms also. It's just that in bagging technique, we just have one model which we will apply in all the different estimators that we're using. I'll showcase you everything in this video, don't worry. Second part of the video means the upcoming video, you will be able to observe that we will be focusing on a concept of stacking, which is also a part of an ensemble technique. And in the third submodule, I would say, we will be focusing on the boosting techniques, where there is a concept of weak learners, and they all combine together to form a strong prediction for the given data. So everything we will discuss in a very detail in the boosting part also, whatever algorithms we have. So this is how the complete module will be created. Now, in this specific module, the specific focus is on the bagging. That what is the literal meaning of bagging? How basically this bagging technique will be done? Is it a constraint that we have to apply decision tree, or can we apply any other model also? I will showcase you everything, theoretically also, logically also, plus practically also. So without wasting any time, let's get started now. So as you all are aware that the full form of bagging is nothing but bootstrapped aggregation, right? I think in the previous sessions also I have conveyed this thing. So the full form is bootstrapped aggregation. So what is happening is, and why it is called bootstrapped aggregation, we will try to understand this in a very layman term. First of all, this reference, this images which I am using while explaining you the concepts is from Hands-on Machine Learning by Orlin, the one which I am referring here for the material preparation. Also, you can also refer that as a standard book whenever you want to see that whatever topics I have covered up, wherever you are feeling that I need more knowledge with respect to that, or I want to do my own research with respect to whatever teaching I have just now done here. So you can just refer that standard book, and all the images, and even you will see the content is also similar, whatever that book is trying to convey. I just want to convey in from these videos in a very layman term, so that it will be very easy for you to understand the stuffs in that specific book. Very amazing book, written by the author. So here you can see this is something which indicates a bagging technique. How is that so? So what is usually happening? We have a training set, and what is happening is, as we are saying, it's a part of an ensemble technique. Why is that so? Because we are doing a random sampling. You can see that we will be having, maybe here we can see 4 models are there: M1, M2, M3 and M4. And in every model, we are taking a random samples. Random sampling is going on. I hope you all know that we have different ways of doing a sampling in stats. So here what we are doing is, we are doing a random sampling, that too with replacement. So what is happening is, it might be the case that similar samples are coming up in the different models as well. And that is where, because all these models, these base model, all of them are same. Either you are talking about k nearest neighbor, or you're talking about decision tree, or you're talking about logistic regression. It will be same only, right? That's the literal intuition behind this bootstrap. Okay. And why it is called aggregation? Because at the end of the day, all these are the predictors. This M1 model will give its own prediction. M2 model will try to give its own prediction. M3 will try to give its own prediction. And similarly, you will be able to observe that M4 will also try to give its own predictions. So what is happening is, each and every model is trying to convey here one specific prediction, right? You can see from this diagram. Now, what is happening at the end of the day? Let's say here we are trying to, convey a classification kind of a problem. So as I told you, why it is called aggregation? Because somehow we are trying to combine all the results. For example, M1 model says that, the class is 0 as a prediction class. M2 also says 0. M3 also says 0. M4 says, let's say 1. So what will happen is, there is a concept of something called as majority voting, which will come into picture, and it says that whatever be the maximum majority, I would say models or predictors will say, that will be the final outcome. Means for this specific case, 0 is the final, you can say, ultimate prediction. 0 is the final ultimate prediction. So this is the overall idea behind this bagging algorithm, right? Now, in this specific case, if you will be easily able to observe, one important thing is that all these models, M1, M2, M3, M4, they should be the same models only. When I'm saying same models, it can be all of them maybe belongs to KNN, all of them may belongs to, you can say, logistic regression, LR. If it's a classification problem, all of them might belongs to decision tree, DT, and so on. Now, one important thing, depending upon what kind of problem you're trying to solve. If it's a classification problem, you have to obviously apply the classifier based models only. If it's a regression problem, accordingly you will change your regressor, right? You will apply maybe linear regression in all of them, or you will apply maybe decision tree regressor in all of them, or you will apply maybe k nearest neighbor as a regressor, right? In all of these models. So depending upon what kind of problem you're trying to convey or solve, your predictors will get changed. Your models will get changed as per the given prediction which you want, right, at the end of the day. So this is the overall idea behind the bagging technique. One of the very, very interesting and important technique. Why it is called ensemble? Because now we are not relying on a single model. We are not relying on a single result. We are saying that we will try to see the results of each and every model, and then we will try to aggregate all of them. That's why bootstrap aggregation came into picture as a full form. If it's a regression specific scenario, what will happen is, it will try to take the average. For example, what will happen in the regression? There will be a continuous values as a prediction. For example, you are trying to solve a problem of house price prediction. So there will be a prediction of, let's say, 2.3 CR. as a flat price. Some model M2 will say that it will be 3.2 CR. M3 will say it will be, let's say, 4.7 CR. M4 will say, let's say, it will be 1.3 CR. So what will happen is, as a final prediction of the house, it will be the average of all of them, mean value, and that will be the final outcome which we will be able to achieve via this regression specific scenario. So this is the ultimate idea behind this bagging technique. Now, I might have showcased you this logical concept in the previous sessions when I was discussing about the random forest also. So whenever we're talking about random forest algorithm, which we have already covered up in our decision tree module, it's a part of a bagging technique only. Always remember, it's a part of a bagging technique only. The only thing is, you will be able to observe that in this technique, we will be able to see that internally decision trees are working on. Internally, decision tree is something which is working on. Depending upon, there is a specific parameter in a random forest called as number of estimators, via which it will be able to give me an idea that how many number of estimators are currently working in a specific model, means how many number of decision trees are working here. I hope it makes sense. So now what I will do is, I will try to showcase you the implementation of whatever I have just now conveyed. For that, and we will see that whether the performance actually improves when we will apply a bagging algorithm as comparable to the normal KNN algorithm. Let's say if we'll take that as an example. So what I will do is, I will try to take one default data set available in our sklearn itself. So what I will do is, I will try to, first of all, from sklearn, I will try to, because it's a part of an ensemble technique, import the bagging. Okay, so you need to import the bagging classifier. Documentation also I will show you at the end of the session. After that, because I'm applying here k nearest neighbor, so you all know that it is available in a sklearn.neighbors. You can import k neighbors classifier. K neighbors, might be spelling mistake will be there. I'll just look into it from the documentation. K neighbors, BORS. HBORS. So here we have imported the required algorithms which we will use here. Apart from this, definitely we need to import all the required packages. For example, frameworks like pandas, NumPy, right? NumPy is NP, matplotlib.pyplot as PLT. And apart from this, we will also import the Seaborn as SNS. So in this way, we will be able to import all the required frameworks. And I think now we are ready to go, right? So now what we can do here is, we can try to load the dataset first. So we will take the data from sklearn.datasets. So I will just now showcase you from sklearn.datasets module, we have a data of breast cancer. So what I will do is, I will say import load underscore breast underscore cancer. Now data is equals to load underscore breast underscore cancer, and with this I think our data should be ready. Let's try to see the data first. So there is, okay, let's try to see the type of this data, whether it's a data frame or not. Let's check it out. It's loaded. Let me try to see the data here. So I feel it's not a data frame, that's why the issue was coming up, but it's completely fine. You can see that one is the data where we will be having a specific records of array type, and we have a separate target key where the target value is available. It is indicating that, whether the patient is having a breast cancer or not, right? Whatever be the number of instances, number of attributes, every information is available here in the form of what are the feature names we have, mean radius, mean texture, mean parameter, mean area, everything is available here, right, in this CSV file. So now what we can do is, we can try to split the data into input and target feature. So what we can do here is, we can say x is equals to data dot. Now inside that also we have a data key only, so we can load that, and y is equals to data dot, I would say target is the key, right? So in this way we will be able to get the target here. X and y will be available to us. X contains all the input features and Y contains the target column here. Right? Now, the next step would be where we will try to split the data into training and testing. So we will split the data into train and test set. So how can we do that? We will simply do one thing: X train, X train, X test, Y train, and Y test. So here we will be having a train test split. Inside that, we will be having a value of X and Y. So what we can do here is we can just simply import from sklearn dot model underscore selection. We can simply import train underscore test underscore split. So it will be done. I think test size and the random state, I'll take it as a default one. And I think our data will be ready now as a train and test set. Now what we will do is we will do two things here in this specific code part. First thing is, because I want to compare the results of this bagging technique, and with that we will able to understand also how can we do the implementation. So what I will do is I'll try to compare the results when I'm doing via a normal K neighbor classifier, and when I'll try to create a bag of that K neighbor classifier. So one thing is, first of all, what I'll do is I will try to create a model of K neighbors classifier. So what we can do here is we can just call our model as K neighbors classifier. So let me just, this is the model name. So inside that, maybe I will take the default parameters, whatever is their number of neighbors as 5. So I'll not change anything. I'll not do any hyperparameter tuning here, taking as a default thing. Now what I will do is, definitely we have to fit that model on our train set that we have, X underscore train and Y underscore train. And once our train set is ready, what we can do is we can just analyze the score of this model on the test set. So what we will do is we will be able to check what is the value of X underscore test and Y underscore test, right? Let's see. So you can see we are getting somehow the score as 91.60. If you want, you can just do the prediction also, X and knn dot predict, and you will be able to get the predictions on the X test. And if you want, you can also store these predictions under Y underscore predict, or you can say Y underscore pred. And if you want, you can just have a look onto that how our predictions looks like. And obviously it's a classification problem, so our predictions will also be like 0 and 1. Makes sense, right? Makes sense. Now, this is one thing which we have done, where we have tried to curate a model of K neighbors classifier. Now, another thing which I will do here is I will try to create a bagging classifier now. So second thing is we will do the bagging technique here. We will try to create a model of bagging classifier now. So what we can do here is we can say bag of KNN, right? Now, instead of using a single K neighbor classifier, I am saying that I will take multiple models that will take internally the subset of the original data that we have, sample of that, random sampling, that too with replacement, right? That's what we have understood so far. So what we can do here is we can try to curate a bagging classifier here. And inside that, we will try to take the model as KNN, right? But here we will define the number of estimators. So we are saying that the number of estimators is, let's say, for now, I am taking it as a 10 for the easy understanding purpose. Remaining things, maybe let's take it as it is. That's the only thing which I am taking it here. Okay. So let's try to see. And after that, we will say again, bag underscore KNN. We will try to fit this model on top of the training set that we have, which is X underscore train, comma, Y underscore train. And after that, we will just check the score of this specific model on the test set again. Let's try to check it out. So here you can see, right, our score has improved. So initially when we are applying only a single normal K nearest neighbor, our score was 91.6%. And when I have used internally that same KNN model, but now I am saying that I will be having 10 number of estimators, means internally in the model, somehow 10 KNN models are working side by side simultaneously, will give the prediction, and then majority voting will be applied. whatever be the, you can say, maximum votes out of 10 my model will be able to get, that will be the final outcome by the given model named as bag underscore knn. If you want to see the predictions again, you can again check y underscore pred underscore bag underscore knn, and inside that you can just try to say bag underscore knn dot predict, and you can just pass the test set here, right? And even you can check the accuracy wala part as well at your end. You can just, I'll share with you this file, you can just play on this file with respect to the different numbers. You can generate the classification report, confusion matrix, whatever things we have learned in our previous discussions of classifier. Please make sure that you will use those things. My task is to help you understand the conceptual part, but there is a lot more which you can do on top of this file, right? For example, here you can see EDA wala part, I have not done anything. So maybe if you will improvise on those aspects, you will be able to get a better results, right? So here you can just clearly see now what is the predictions we will be able to get here. So you will be able to understand here, we are getting the results at 0, 1, 1, 0 and so on. So in this way, we will be able to get the predictions in both the ends. So somehow one thing you definitely have observed here, which is that as we are approaching from a single model, as we're approaching from a single model to the bagging model, I would say what is happening is that somehow we will be able to enhance the accuracy of the given model, right? We will be able to enhance the accuracy of the given model. Now, this is the beauty about bagging techniques. That is that if let's say your model is having an overfitting problem, for example, that is what the advantage of random forest we have seen, right? When we were applying a normal decision tree, overfitting problem came into picture. But as we shifted towards random forest, which is taking internally multiple decision trees, the problem of overfitting was not there, right? So it somehow decreases the variance, and which basically helps my model to avoid that overfitting and reducing variance without any increasing in the bias part. In all, we want a we will be able to get a ideal, or you can say perfect model, in other words, right? So in other words, I can say it will be able to reduce the overfitting problem in a model, in a model. Apart from this, you can also observe that somehow it is computationally you can say cheaper task as comparable to training the complete whole data set. Why is that so? Why I'm saying this thing? Because see, what is happening is here we are taking a random samples which are somehow the subset of the complete data set, right? Subset of the complete data set that we have. So what we are doing is we are trying to curate a random samples, which is nothing but is a subset of data. So we are not at a time of training passing the complete data set. We are taking a random samples, and that is what we are passing there. So obviously, computationally, it will become more cheaper as comparable to training the complete data set altogether. So all these are the, I would say, pros of using the bagging technique. But with every pro, it comes a cons as well. So what is the disadvantage or cons of using a bagging technique? One major thing is the interpretability of the model. Interpretability of the model. This is compromised. Why? Because now see, internally, when we are trying to curate a single decision tree, it will be very easy to understand, right? Interpret that how the model is working, how I was able to get that Gini value, how I was able to get that entropy value, how that at the end the Gini value will become 0, means we will be able to get a very pure sample. But as soon as you're increasing the number of estimators, now not a single decision tree is working. Multiple decision trees are working. Example is random forest, we have already discussed, right? Same thing is happening for this example also, where initially we just have only one canon working. But as soon as you increase the number of estimators, it's very difficult for us to understand that how the internal things are working on, how the calculations are going on. And that is where this is compromised. Interpretation of the given model is compromised. If only single model is working, it would be very easy to understand that how things are going on internally. It was not a black box for us. But as soon as we are increasing the number of estimators, we are approaching towards the bagging techniques, that interpretation is not that much easier task. That is the only cons that we will be facing when we are applying the bagging technique. Otherwise, everything is so good, and whatever be the advantages we will be able to get, I have showcased you with the implementation itself. So I hope that this bagging stuff is now clear to everyone. Now, in this specific case, I have showcased you the example of a neighbors classifier, right? In a classification model of a cancerous data. But definitely at your end, you can apply any other model also, and you can see the performance. Maybe you can apply logistic regression, single model, and then you can apply a bag of LR, logistic regression. One thing you have to make sure that whatever models you are applying, in all these models, the algorithm working will be same. Means you cannot apply that in one M1 you will apply K neighbors, in another M2 you will apply logistic regression. This is not how things will go in a bagging technique. If you wish to apply different models altogether, that is also possible, which we will cover up in the upcoming video. And that is called as stacking, which we will cover up in the upcoming session, where you will see that if, let's say, I want to see the beauty of different algorithms applying and the applications of that, and will that be helpful, will that be able to give a better result as comparable to this one, everything we will see. Just have a patience on that part. But in the bagging, all these models will remain the same. Okay. So I hope that now you will be able to get the clear understanding of what is the meaning of bagging, what is the full form of that, what is the internal intuition behind that, how basically we can do the implementation for the same, and how this will be able to help us in order to improvise the results, in order to reduce the overfitting. When I'm saying reduce the overfitting, it simply means that it will try to, you can say, reduce the variance without increase in the bias. That is the literal intuition, I would say, behind this reduction of the overfitting problem part per se. So I hope this much part is clear. And at the end, we have seen computationally also, it will be really helpful. The only con is that interpretation of the model is really difficult, as we are increasing the number of estimators, we are increasing the number of models which are working internally. So now I hope that you will be able to get a clear-cut idea behind the bagging technique, which is a part of an ensemble one. In the next upcoming video, we will deep dive into stacking part and how it is different from bagging. It's one of the very widely asked interview question also, that what is the difference between bagging versus stacking versus boosting, which we will cover up in the next video. So please make sure that you will be able to understand all of these concepts in a great detail. And with this, I will see you all very soon in the upcoming videos. Bye bye everyone, and see ya.